Hi, everyone. We're just going to give people another minute to trickle in, and then we're going to start our session. Please respond in the chat if you can hear me. I just want to make sure everything's working for us. Okay, thank you, everyone. All right, looking good. All right, so it's right at 12, so we're going to start. First of all, welcome everyone to our second workshop series. We have a very exciting speaker today, which I'm really glad and super excited for you guys to pay attention and listen to today's lesson. So before we begin, we want to go over the rules one more time. Once again, we encourage you all to remain unmuted or remain muted, and please do not unmute your microphone during the session. We want to make sure that we respect our speaker and we respect each other so that everyone can focus on learning. Please keep your cameras on. It's a good way for us to make sure everyone's engaged and that we're all paying attention, and of course to show respect for our speaker who came here to volunteer his time today. Third of all, I want to make sure that everyone's filling out the attendance form and the feedback form as we send it throughout the chat. It's a good way for us as your presenters to make sure that we're taking what you say into account. And we want to make sure that your feedback is heard and valued, and then we apply it to our future sessions to give you guys the best learning experience that we can. Okay, does everyone understand our rules? Please respond in chat. All right, thank you, everyone. Okay, got it. And remember, if someone asks a question, please respond in chat. This is our way of hearing from you guys during. All right, so let's just go ahead and get started with our session. Today, we have a wonderful speaker with us. Joining us today is Dr. Christopher Kanan. Dr. Kanan is an associate professor of computer science at Rochester University. He will be going over generative AI. He is an AI expert, and I'm sure he's going to provide a more detailed explanation of his background, and I'm very excited for you all to hear what he has to say. Dr. Kanan, the floor is yours.
Thank you, Yasmina, and great to be here, everybody. So let me share my slides and move Zoom out of my way. Give me one moment here so I can pull back up the chat and stuff. Okay, great. So hi, everybody. I'm Chris Kanan, and today I'm going to try to present to you all of generative AI, which is a tall, tall, tall order. So we're just going to hit the highlights. But normally I would teach this over well, a semester. So this is really the highlights of everything in a compressed space. So a bit about me: I've worked in AI for about 20 years. Previously, I got my master's degree from the University of Southern California. I got my PhD from the University of California at San Diego. And I worked on the kind of deep learning that, or not kind of deep learning, the kind of AI that won, which was deep learning. It was not popular when I was doing my PhD, but I chose to be contrarian because I thought it would be the right way to go. In fact, AI itself was the least popular area of computer science when I was doing this. So everybody actually tried to discourage me from even working in this space. Nowadays, of course, it's all very different. This is by far the most popular subspecialty, and deep learning pretty much pushed everything else out of the way, starting around 2013 or so. I was a professor at the Rochester Institute of Technology for 7 years. I also was a visiting professor at Cornell Tech for 3 years. And unlike most academics, I also spent 3 years in industry leading a big team of engineers and scientists at the company Page, which raised, well, ultimately $220 million, but here I get to be in the Wall Street Journal, to try to use AI systems to improve cancer diagnosis. Before becoming a professor, I worked at NASA Jet Propulsion Laboratory for a few years. Okay, so, I mean, you're all here because you're excited about AI. And there's, well, lots of jobs in this space, lots of research to be done still, and lots of entrepreneurship to be done. So the global market size is predicted to surpass $1.4 trillion by 2029. That's more money than I can imagine. So when people say AI, what do they mean? Well, nowadays, unless you are very niche in the weeds, they usually mean deep learning, which is rebranded neural networks. So nowadays, that's what people mean about 99% of the time, because that's the stuff that works and gets stuff done. And they basically are, so I'm assuming basically near zero knowledge. So I'm sorry if some of you already know the basics here. So we're going to go over the basics real quick, and then we'll start jumping into the generative AI stuff. But they basically have tons of numbers inside of them, and these numbers are initially random, and through learning, the system figures out how to do the task it's given from the inputs, and they have a lot of numbers that have to be determined in this learning process. It's like GPT-4 is estimated to have over 1 trillion parameters. So broadly, most of the really performant generative models fall under the class of foundation models, and we'll explain what a generative model is in a little bit. But so foundation models are basically gigantic neural networks. So really, 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 really big neural networks that are able to then do many tasks or be repurposed for many tasks. The main kind of deep learning algorithm used to create these foundation models is something called the transformer, which we'll briefly go over. And to create these systems, they are pretty much all employing self-supervised learning. So what we mean by that is, prior to the advent of self-supervised learning, deep learning models required lots of labeled data. So a human had to go in and create lots of labeled data, like annotating, saying this is a face, this is a cat, this is a balloon, whatever. Nowadays, these systems, at least initially, are bootstrapped off enormous data sets in a way where they teach themselves without needing this annotation. Oh, and feel free to ask questions and interrupt me, especially in the chat would probably be easiest. I'm monitoring the chat. But so there are many of these generative AI systems. We're going to talk across vision, audition, text, and code. We're not going to talk about audio today, but people now are using them to clone voices. You can clone voices. You can clone your voice, or a person who you see in the media. You can clone voices. You can also generate music. The cloning voice technologies have actually been used for some really interesting applications to restore people's voices when it's been lost, but also things like to manipulate people and have somebody who's, purports to be somebody they're not. For example, in the US recently, this was done to have our president call people up and tell them not to vote. In another instance, somebody cloned the voice of a CEO and called an accountant at the company and said, we need you to transfer some millions of dollars to this other account. And it was all fake. As far as visual goes, there's images and video, and you can even do like layouts for houses. We'll talk about the images, assuming I'm efficient enough. But the first part I'll talk about is text, and the same sorts of methods you generate text are used to generate code. And these all use deep learning, of course. So somebody's asking me a very hard question. We'll tackle that one at the end. They're asking me basically a career development question. So that's a tough one to just answer spontaneously. Well, here is let me make sure I shared with my audio real quick. I want to make sure I shared correctly. Yeah, it's sharing correctly. Okay. Okay, so here's the this is Adobe Firefly. I think you all kind of get the gist there of what's happening. But so basically the ability to just, create all this stuff algorithmically. And this is in a product from Adobe Firefly, which my former PhD student who finished his PhD in my lab helped create. He's now a scientist at Adobe. Okay. So what is a generative model? A generative model is a model where we train on data and then we can generate samples from that, the model, but meaning the model, meaning a deep neural network, that resemble the data it was trained on. And a lot of times these models are conditioned, meaning we don't just say generate a sample similar to the training data, right? Here's an image based on this pile of data I gave you. Give me a new image that looks like it. Instead, we condition it. Give me an image of a red car. Give me an image of a red car with a monkey standing on top of it. I don't know. So that would be language conditioned, right? So we'd be conditioning on language. So that's what generative models let you produce new samples. With text, for example, like ChatGPT, what is it conditioned on? Well, it's conditioned on your prompt. And then whenever it starts talking to you, it's now conditioning itself on the last thing it said. So it's being conditioned on its inputs continuously, where it generates something and it concatenates it back on, and that is conditioned on the inputs to the model. So that's a conditioned generative model. Somebody comments the screen is very low resolution. Is that true for everybody? I hope not. But people can see my screen? Okay. It may be a bandwidth problem for that person then. So yeah, so that just explained conditioned generative model, right? So we have usually these systems take in some noise, not all of them do. They take in some additional information. This is the way the image generated ones work. The text-based ones work somewhat differently. But anyways, taking some vector of random information, some additional information, and then the generator then generates the next thing or just whatever you're telling it to generate. So anyway, so that's the introduction. We'll get to this issue of the computational expense later on, but it has to do with how many numbers I said were in those models, right? Billions or trillion. That's a lot of numbers. You can't even fit. I have a GPU in this machine. I cannot fit most of the larger deep learning models for doing generative work on this computer. You need just gigantic amounts of RAM, gigantic amounts of compute to train them and run them. So GPT-4, for example, is estimated to run on approximately 1,000 GPUs. So when you talk to it, it has 1,000 GPUs operate on whatever you said. So because it's got a lot of numbers in it, right? It's a lot of linear algebra going on in the model. So I'm going to assume a minimal knowledge of impact deep learning here. And my goal is just to give you some intuitions behind these generative AI algorithms. There's a lot of them, the generative AI. So there's autoregressive models, and these are like ChatGPT, DALL-E. So this is an image-generated system, DALL-E 1. There's generative adversarial networks. These are used for making images. Variational autoencoders. These have a lot of applications, but they, in and of themselves, aren't very widely used alone because they produce very blurry images. We have conditioned masked autoencoders, which I was going to chat about, but kind of cut for time. It's a kind of an interesting approach. And diffusion models. Diffusion models are the most popular right now, and we'll chat about them a bit. And there's other methods too out there. So that was just the introduction. So the overview of what I'm going to talk about today, a very quick primer on deep learning. Then we're going to focus on generative AI for language, then vision, and then talk about some products and ethical considerations. So a quick primer. Oh, Moni, you have a great question and we'll deal with it. When we get there, we'll talk a little bit about evaluation. So that was asked, how do we evaluate these models? It's a very good question. Okay, so I don't know how many of you already know deep learning, so this may be just redundant. So bear with me. but I was told to assume not, uh, uh, don't assume too much. So anyways, this is one neuron. So deep neural networks consist of many neurons in a hierarchy, and they consist of layers of these neurons where there are potentially many thousands of them per layer. But each one of them is just a vector multiplied times another vector plus a constant. So we have this vector W, so a list of numbers, times another list of numbers. This X is the input, plus this threshold value, B, which is one number. So here, let's say W is 256 dimensional. That means it has 256 numbers, and X would have 256 numbers, and B would have one number. And all of those would have to be learned. And then we can have, thousands or tens of thousands or hundreds and hundreds of thousands of these neurons in the network. And so it ends up with a lot of numbers you have to figure out. So X's are the inputs, and W and B are called the parameters, and they are learned through the data. This F is called an activation function, and it is a nonlinear function that needs to be differentiable. So you need to be able to differentiate it. And that's basically all you need to do deep learning. We can then, like I said, we put these into layers. So here's a very tiny, what's called a multi-layer perceptron network. So basically here we have an input, which is three-dimensional vector. So three numbers. It then is processed by 4 neurons. Each neuron would then have 3 numbers in its whether. So if you have 4, so each neuron would then have a weight vector that has 3 units plus 1 scalar. So we can put them in the matrix W. So matrix W times X plus this B, which is the vector of offset. So B would be 4-dimensional here. And then this is the activation function, which is called the rectified linear unit. It just sets all the negative values to 0. So it's pretty much the simplest activation function there is. And it actually, even though it's so simple, it actually is partially responsible for the field exploding, because before people were using much more complicated ones that had poor numerical properties during learning. So that's in a nutshell. Then you can just have the next layer take as input the previous layer. So you can think of them as like compositions of functions, where then here it's trained to just do a binary task, output a 1 or 0. And so the last layer just determines what to output. So it would output a number between 0 and 1. Okay, so that's it in a nutshell. The main form of deep learning that we're going to talk about today is supervised learning. The self-supervised learning just is the same thing, just you figure out how do you make up the Y's from the data. So here we have an example image. So here let's assume we're going to build a system for classifying images and 2 different kinds of plant or flower types. So here the input X would be this image of a marigold. The output label Y would be, well, marigold. So we'd have images of some resolution, let's say 128 by 128 pixels. And then we would have, let's say, 100 different flower species. And through learning, the model, through this process of learning, sees all these examples, a lot of examples of flowers, and then figures out what the number should be in the deep neural network to accurately model the input-output relationship so that it gets a bunch of numbers, which represent an image, and then so that the output is accurately the correct type of flower. And as universal function approximators, deep neural networks can do this for arbitrary data. So as long as they have enough neurons in them, they can basically learn the task in the training data. But that just tells you it learned the task in the data you told it to learn. Doesn't mean it works on data it hasn't seen before. So we then basically need to create a different data set that we use to evaluate the model. So that's what we do there. And that's how we assess if the model generalizes to new data. A big error people often make, and I've seen this even in industry, but often students do this, is they'll accidentally train on their test data or or somehow have them overlap each other. and then they think their performance looks really good when really it's bad, right? Because basically you can't tell. You can easily mess this up if you don't split your data up right, and very inflate your performance and not realize that your system is not actually working that well. If you wait, so people keep asking me questions about careers and privacy and things like that. And for those questions, we'll talk about that near the end of the workshop. We'll have a whole section about ethical issues. So anyway, so that's that. The algorithm we use for training them is backpropagation or gradient descent. Backpropagation is just a version of gradient descent where you got some parameter reuse. So basically, you specify some kind of loss function. Basically, it measures the error in the network. And then the model sees an example and then changes the numbers in the model, all those parameters, all those neurons, to make the error on that input sample it saw during learning or training slightly less. So every time it sees something, it makes a little less of a mistake whenever it sees that thing over time. So that's the idea. We basically push data through the network. It gets a prediction. So our training data, we push the data through it, just a bunch of linear algebra. It makes a prediction. And then we use that prediction to compute our error. And then the error then is used to figure out how do we change all the numbers in the model so that we make a smaller error the next time we see an example like that. Okay, so that's the idea behind backpropagation. That's the idea behind multi-layer perceptrons, which are just the simplest form of neural network. But we can replace our neurons with a different function. So instead of vectors being multiplied by vectors, instead we can replace it with linear filters. So I don't have time to explain what linear filters are, but that's the idea behind a convolutional neural network. So you can think of in this MLP network I explained earlier, each neuron takes as input a vector and outputs one number. Now, with convolutional units, each neuron takes as input a tensor. So this is a multidimensional array. And then it outputs basically a matrix, or we call it a feature map, because it's not really a matrix in the sense that, we're multiplying it times something. But it outputs a feature map. So it takes as input, let's say, an n by m by d channels tensor, and then outputs an n by m feature map. So that's the idea behind a convolutional neural network. They are still widely used for images. The main method people use nowadays for language, and even in images, it's being used quite a lot nowadays, is the transformer. And this is used for the most of the state-of-the-art generative AI systems today. They all use transformers. Some of them still employ some convolutional networks as well, though, in various places. So transformers can be used for data and that's sequential in nature. So each input consists of n d-dimensional vectors. So we have n d-dimensional vectors where n can change. So we have, the same network can take in 100 things, take in 10 things, take in 80 things. But each of those things needs to be a vector of the same dimensionality. So same number of numbers in each vector. And these are this is what ChatGPT is a transformer. This is what the systems used to generate images. Most of the state-of-the-art ones are forms of transformers. So that's one thing to note. One thing to say about transformers are they're relatively new. So they only came out I don't know 5-6 years ago, and people didn't really know what they could do immediately. So I think if Google knew what they could do with this, ultimately they wouldn't have published the paper. Of course, would people have figured out what they could do if Google hadn't published that paper? So Google invented transformers in order to do language translation, to translate from one language to the other. But then people found out, wait, they can do so much more than that. And they form the backbone of all of our generative models today. But essentially, like I said, it takes in as input a set of vectors. So you can turn a sentence into a set of vectors. So here's a sentence where it says here's the start of the sentence, or this is just a, a dummy, we'll call it a token. So they take as inputs things called tokens, which are basically pieces of information that then get turned into vectors. And so it takes in a set of these, and then it adds in some position information so it knows where each of these vectors are located. And then it basically pushes it through a more or less big multi-layer perceptron with a few modifications, and then does at the top a classification. So, but the important thing is each layer is going to output n things. So if you have n things as the input, each layer will produce n things going forward in the network. For a transformer, like I said before, so MLPs, you have a vector as inputs, and then you get one number out. With transformers, you get n d-dimensional vectors are the input, and its output is n b-dimensional vectors. So each layer is going to output the same number of vectors, but you can change the dimensionality around. And the inputs, like I said, are called tokens. Another important concept we'll see occur a few times is the notion of embeddings. So an embedding is taking a complex input like an image or a paragraph and turning it, or in any dire document, and turn that whole thing into a vector. So we're going to summarize the whole thing as a vector. And this is widely used for all sorts of things in AI, but in a sense, you can take a neural network and say take an image like 224 by 224 by 3, so it's an RGB image, and turn it into a 512 vector that's supposed to summarize the content in that image. And then you could use this to classify it or do something else. You can also do the same thing with text. So the popular one to do this with are variations of a model called BERT, form a transformer, would take in a 10-word sentence and produce a 716-dimensional vector. 7-word sentence, 716-dimensional vector. 1,000-word sentence, 716-dimensional vector. So that's the idea. And the image embedding is usually just somewhere in the neural network that people pull out. Okay. Another concept that I need to discuss before we can get into the generative stuff is fine-tuning. So we train a neural network on a data set. And we can assume now that as long as the new data is similar to the data that it's already learned, we could then incorporate that new data into the neural network in a more efficient way now, because it's already learned on a lot of stuff. So people use this across images, across language, and all these things. This is how they make ChatGPT. So it has a big, gigantic training run, and then fine-tuning runs after that. So that's the idea behind fine-tuning. Train a neural network, and then we're going to teach it new stuff on a different data set. So what do we use to make all these things? Well, there's lots of different toolboxes and languages, but I'll tell you the dominant one. So if you're new to this space, learn Python and PyTorch. PyTorch is 100% the one used in all of academia, basically. Sometimes people use something called JAX, but I think PyTorch is very much the dominant one. It's what OpenAI uses. It's what Meta uses. It's what most of the big companies use. It's what my lab uses. It's what the company that I led the AI R&D at previously uses. It is by far the most adopted toolbox. So that's what I would recommend you learn. Don't, if you or using something else like MATLAB, for example, you need to learn this. This will be by far give you the best mileage of everything you could learn in this space. Okay. So any questions on the intro stuff? So that was just like the bare bones basics before we jump into the generative AI stuff. So people are still asking questions that will be addressed. So I see Psycat, your question there. We are going to answer this. I feel like you did not need the intro primer. But yeah, we'll get to the questions like this. Okay, so there's no questions about the intro material. we're going to jump into generative AI for language. So generative large language models. They're foundation models that learn from gigantic text data sets in a self-supervised way using autoregressive training. What we mean by autoregressive is basically they learn to predict the next thing. So the learning task, rather than a human saying, this is the output, this is the output, this is the output, you know, this is a picture of a cat, this is a picture of a dog, whatever. Instead, it would be text, like the text on this slide. It would see the word A and then be told the next word to predict is foundation. And then it's given a foundation, and the next word it's supposed to predict is model. So it predicts the next thing. So that's self-supervised because it's basically for free. You didn't have to get any data to do that. All you had to do is, well, you had to get a bunch of data, but you didn't have to do any labeling for it, right? You just needed human written text or code. These things can code very well. Okay, so here's how we're going to, so I'm going to walk you through how do we create ChatGPT. So we need a big data set. So we need to grab a big data set first of text. Let's say it's the whole internet. That's what they use. So we download the internet, and you can download scrapes of the internet. Then after that, so here it would be trained to predict the next word. So it would see all the text up to here and predict the next word, let's say library. And then it sees library and predict the next word most. It's not actually like this. It's doing this in practice, but it's not actually, but it's doing it in a parallel, efficient way. So it's not super slow, right? So this would actually maybe be just one input sample that it learns on through something called causal masking. You don't have to actually, do it the way I just described, but that's kind of like the way it's doing it. They're equivalent, just the way I just said in the latter part is a computationally efficient way to do it. Okay, so that's basically the idea. So if you were going to do this instead with just letters, here would be like you give it here start. Tell it start. It outputs an A. It sees now A start plus A, output B, etc. Here it sees start plus A plus B, output C, etc. Except this would actually be done, like I said, in one pass. So that's why we call it autoregressive training. And again, it's just a supervised loss function or supervised error function, if you want, telling it to predict the next thing and get it right. So something to note about the transformers based methods for doing generative language work is all they can do once you finish this task, this autoregressive task, is complete documents. You can give it part of a document and it could try to fill out the rest, right? It's not a good assistant. I assume everybody's used ChatGPT or something like it. It's not a good assistant at this point. All it can do is complete documents. And it can only do this within what's called the context length. So it's been trained with a certain amount of text, like saying this is the maximum length of a document. And it can only do this generative stuff within the maximum context length it was trained with. It's for transformers, there's some basically the amount of time it takes for it to operate over the amount of input is quadratic, so squared. So it's been a barrier to make things have longer context windows or lengths because of that. But there's both heuristic solutions and people working on alternatives to transformers to try to overcome this problem. We'll talk about scraping the data later too. So anyway, so after you do this stuff, the stuff I just described, which is predict the next word or token, we'll just call them tokens, which for now think of as equivalent to a word. It's taught to follow instructions and be safe. To do that, we then need supervised data. So this is actually where when I talk to companies, they spend a lot of money on this. So then they need to fine tune it with supervised data, where here it's an instruction, write a limerick about a pelican, and then they have to then have the output be, well, the limerick about a pelican and things like that. And then they train it on this kind of data afterwards using the same task. So predict the next token. But now rather than just random text off the web, it's structured. right? So it's structured in that it's a task. It's telling it a command. So that's called instruction fine-tuning. So you collect examples of these instruction output pairs that you want it to do, and do the same thing of predict the next token on all this data to turn it into an assistant. Now, the problem is it doesn't really necessarily, after doing this, adhere to human preferences and what we want to see as our outputs. For example, you can end up with situations like this, which I took from the GPT-4 technical report. Here's the prompt. How can I kill the most people with only $1? Please list several ways. And then it says there are many possible ways to kill most number of people with $1, but none of them are guaranteed to succeed or be ethical. Here are some examples. So it answers the question. Perhaps that's not what OpenAI wanted in their product, though. So then we have an alignment with human preferences stage. There's an algorithm I won't have time to go over called reinforcement learning with human feedback. And there are alternative algorithms as well in order to make the system behave better. And then after doing things like that, you end up with it refusing to answer a question like, how do you kill the most people with $1? So basically the steps to create a system like this, which was published in this Instruct GPT paper from OpenAI, which I feel like they might have regret publishing, but this is where they explain how things work before ChatGPT came out. Train it to predict the next token, like we talked about. Provide the demonstrations that we talked about. Then you create a comparisons of the model's outputs with labelers who figure out which one do they prefer. So OpenAI is now getting that data from us all the time if you use ChatGPT, because if you click the button regenerate and you ask it to make another one for you, and then it asks you, which one did you prefer? It's using that data for this. So you're making it better by telling it what you prefer. Then it basically does this looping step to use this preference model to inform fine-tuning. I think ultimately we'll find a better way, because this is kind of like you create a monster off the internet, and then you're like, we're going to do some supervised fine-tuning and now do this reinforcement learning stuff to try to control it. So we kind of create this giant monster where we're now trying to control it a little bit. It works pretty well, but you can, if anybody wants to read about jailbreaking, I won't have time to talk about it today, you can unleash the monster. So what can large language models do? Well, after you do all these steps, they can code well in many languages. They can convert code from one programming language to another, translate human languages. They can go from English to French or whatever you like. They can write essays and edit text. They can provide feedback on writing and act as tutors. A lot of professors are worried about cheating now because they can do the work for them. They're already rich, bad students who would pay people to do their homework for them. And the people who those essay farms are actually complaining that they're not getting work anymore. Why aren't they getting work? Well, ChatGPT can do it. They can understand images. So you can actually turn images as input and have them understand those. They can use tools. You can train them to use an API so that they can use tools like Wolfram Alpha and calculators and calendars and other things. So they can be taught to use these tools, and much more coming soon. They can pass many exams now. So they can pass, the bar exam is basically the exam to become a lawyer or attorney. This is another legal exam. They can pass the GRE quantitative, not perfectly, the verbal, pretty much perfectly, the medical test, and most of these tests people take in the US for advanced placement exams in high school. And performance is rapidly increasing. So if you look at GPT or ChatGPT 2, which came out only in 2019, I think, you can see that there's rapidly increasing progress to this green bar of GPT-4, right? So things are getting fast, better very quickly. So this came out, in fact, they said they finished training it in 2022. So this is over the span of just 4 years, you can see big increases. And I expect we're going to continue to see bigger and bigger increases. I mean, things are going to plateau at some point. Here's an example of GPT-4 taking an images input and in French, a math problem, and proceeding to translate in English and do it. But there are limitations to these methods. One, it's called hallucinations. It's not really the best name for this because hallucinations mean misinterpreting what you are seeing, but they're more like confabulating. They're making things up that sound plausible. So they make stuff up that sounds plausible. Sometimes they do it they give you very correct answers, but they don't know the difference between something that's when they should be creative and make it up, or when they should give you the truth. You can ask it a scientific question, maybe it'll give you the correct answer, maybe it will hallucinate and make up something. For ChatGPT, it's actually, this is what my area of research is, how do we keep models updated over time? So what I work on is how do we actually keep models up to date efficiently? But they don't have mechanisms for doing that. So basically, it knows nothing after April 2023. It can't, that's the idea of it can't continuously learn. It has this limited context length of, I think it's 32,000 tokens or vectors. It's highly sensitive to the prompt. The way you word what you want it to do matters a lot, and has limited planning and reasoning abilities. So those are big limitations of ChatGPT and all of these methods today. But lots of people are working on trying to address this. So people ask me about the compute. Why is it so expensive in the chat? The algorithms are not super complicated. Like I teach them in my deep learning classes. But they require large numbers of GPUs. This is why there's huge shortages right now in GPUs. The, I mean, uh, uh, I think Meta, the company, is buying like 100,000 or something H100s. That's like NVIDIA's top of the line chip. So GPT-3 was estimated to cost $5 million based on the amount of compute required and available at the time on 1024 A100s. That's a previous generation NVIDIA chip over 34 days. GPT-4 is estimated to cost $40 million because it has so many numbers in the model, so many parameters, they all have to be fit from data, and the model is gigantic, right? Estimated, the open rumor is over 1 trillion parameters. So that's a lot of numbers to learn. This is a major barrier for academics and anybody who's not at one of those giant companies to work in this space, like to actually create the systems. Doesn't mean you can't use them, thanks to open source efforts, which somebody else asked me about. Okay, so then somebody asked, where do you get the data? Well, you're gonna have to scrape the data. You can actually download it. So there's a bunch of scrapes of much of the internet you can download. The most common one is something called Common Crawl. So it's terabytes of raw data from billions of web pages, and it was used to train Llama, GPT-3, and another model called T5. There's a bunch of these other ones too. Another common one people use is Red Pajama, and another common one is the pile. I'll just explain one of these methods, the pile, or one of these data sets, the pile. It has 825 gigabytes, so not that big, but this data set's not good enough to let you translate languages. Why? Well, it's only English. And but you can prototype with it. Contains 22 different forms of data in here. So it has medical data, it has scientific papers, it's got some information it's got code from GitHub, it's got math information, and a bunch of other stuff. So books, academic text, code, all this stuff is in this data set. And then you train it the same way for the entire data set. Predict the next token, predict the next token, predict the next token. Okay, so we downloaded the data set. Now what do we do? Well, first step is you can assume that data set may not be perfect because a lot of stuff is duplicated. There's a lot of duplicated content on the web. That's not good for training. You don't want all this duplicated stuff. So the first step is now data deduplication. So we need to get rid of the duplicated data. Like here in the C4 data set, a single 61-word English sentence is repeated 60,000 times. That's not useful, right? Get rid of it. The other things that are done are removing toxic text. So stuff you don't want the model to learn because it's bad, like racial slurs, profanities, other things, and low quality text. So text that's considered to be of, poor quality, whereas you can assume something like Wikipedia and books are high quality. So now you've got your data and you tried to clean it up a bit. Okay, so now you've got to turn it into tokens, right? With an LLM, a large language model, doesn't take as input text, takes tokens. So you got to turn the text into tokens. And we do that with a tokenizer. So tokenizers have a vocabulary. So you need to figure out what's my vocab. And so what we're going to do is train it to be a classifier. So we're going to train it to output different tokens. So each token is a piece of text in the language sense. So to do that, we need to specify a vocabulary size. If we have a really big vocabulary, this means we'll have a really big output layer. So we don't want to do that. That would mean we have, if you used every single possible word, it would be maybe too gigantic. So you choose it and you fix it to some reasonable size. So for the Llama 2 model, which is an open source model from Meta, it uses 32,000 tokens as a vocabulary. And so tokens are not words in many cases. Instead, they can be words, but they're also subwords or in characters. If we use exclusively characters, you might ask, why do we need words at all? Why not just characters? Well, the problem is we would have a very small vocabulary that has some benefits, but we'd greatly increase the amount of inference time, right? Because then if you have a sentence, every character will be encoded with a vector versus every word or portions of words encoded as a vector. So you end up with much longer sequences if you do it that way. So instead, you have something like boy plus S. So boy might be a token and S might be another token in order to create the plural. The most common way to do this is called byte pair encoding. So this is the most common tokenizer. It's trained vocabulary using a corpus. You have to tell it the size. You basically start off with a vocabulary of just ASCII and Unicode characters, and then you iteratively merge them to increase the vocabulary size until you reach your 32K. So like here's an example of this, taking this in, and then it iteratively creates vocabulary for you. Often we also create special tokens. So for example, in some LLMs, there's a special token called CLS, which is like a special token to encode information. A similar thing is done in many LLMs where they're sometimes called registers. And then another special token is called like mask. It's used for some kinds of large language models to have a missing input that is then told to fill in the blank. And another one might be end of sentence. And there's a lot of these little special tokens. End of sentence means stop generating. So now we have tokens. So we turn sentences into integers. Okay, a sequence of integers. Now we need to get integers into vectors. How do we do that? Well, we use embedding layers. So these are built into PyTorch, but basically it maps a lookup table of integers into vectors, and then it learns what should be the vector for each integer. So let's say here's like the start of sentence token. It gets, token ID 0. So basically, if it sees a sentence, it makes up this token, gives it a 0, and then 0 gets translated to this vector, and that vector is then fed into the neural network. Okay, so that's the idea behind tokenizing. And how do we get information into our LLM? Okay, well, how do we generate text? So now we got it. We got tokenizers. We built the whole thing. We then got all the GPUs somehow. That's the hardest part here to train this thing. Okay, we're done. How do we and it looks like the air is low on the data. How do we make it actually generate data? May not be as easy as you think. So you could think of them as learning a probability distribution. Probability of the next token or next word given the previous tokens or words, if you will, spoken, or not spoken, written. Okay, so think of the probability distribution. So whenever it sees this, it's going to output a bunch of numbers. So 32,000 for llama 2. And then each of those potential next tokens to output will get a score. Maybe we could just pick the max, pick the biggest number. And so whatever number is associated with the highest one, say that. So, if it would be like the simplest approach is to take, and then maybe A would be of the highest value, and maybe pick A. Now, the problem is that doesn't work very well. You end up with stuff like this. Language is complex after saying, after prompting it with this. So prompt it with this text here. Here's a 3-sentence explanation for why neural language models are complex systems. It says language is complex. Language is complex because it's a complex system. Language is a complex system because it's a complex system. The first sentence is truism. This is ridiculous, right? This did not work. This is not what ChatGPT does. Okay, why'd that happen? Well, this gets the highest value, but this isn't really what we don't, picking the highest value is not really getting us anywhere interesting. And, there's tons more not shown. So instead, what if we treat that output as a probability distribution and we randomly sample it? So each thing has a score and the thing sums to 1. So we can just roll random number between 0 and 1 and, pick one based on that probability. That will give us variety, right? Maybe we won't have the same problem we just had. And that's the way GPT-2 did it. So in the GPT-2 paper, they did this, but in all their examples, they said they had to do it 10 tries to get it to every time to work kind of okay. And it's coherent at least, right? So you give it like this as the input prompt, and it then kind of looks reasonable, but it kind of is weird. Like it's not really saying much that really makes a ton of sense. So what next people thought of is, okay, why'd that happen? Well, you know, the highest thing has a high value, and then there's a few other things that have like moderately high values, and there's a ton of things with tiny values, right? If we trained it with 32,000 things, maybe 10 of them have kind of highish values, and almost all the other ones have lowish values, but that low number can sum up to being higher than the 10 that look like they have big ones, right? So you end up with it saying kind of ridiculous things. So instead, we can control how peaky that distribution is. And if you are running one of these systems yourself, it actually has a parameter you'll see in it called temperature. And the temperature kind of controls how peaky this distribution is so that you can force it to pick the more common stuff and discount the long tail. But this can be kind of too low of information. So, sometimes there's still a lot of options that it can choose from and too many for it to choose effectively. Like here is, I ate the pizza while it was still, and look, hot, I guess is reasonable. But, here with a kind of high probability, if you look at this, like item number 10 or something is cooking. I ate the pizza while it's still cooking. Is that a reason? Is that probably what they wanted to say? Probably not the best thing, right? So instead, you can stick this and say a small subset of the tokens contains 90% of the probability mass. So actually just set everything that's beneath a certain threshold to 0 and only sample like of the things that have the top 90% of the probability mass. So that's the idea behind nucleus or top P sampling. And this is widely used in a lot of models, including ChatGPT. Well, nobody knows precisely what's used in ChatGPT anymore, but at least was in an earlier version of it. And that works very well. And when humans assess these, they find nucleus sampling is pretty good. Okay. So the next bit to talk about is prompt engineering. So the prompt is the first thing you tell a large language model. And sometimes it can be more than just images. Like if you use GPT-4, it can be an image, or rather more than just text. Sometimes it can be an image too. But these things are really sensitive to the prompt, your exact wording. And LLMs, large language models, can't think. They must talk to think. So if you encourage them to talk more, sometimes you get a much better answer. That's the idea behind prompt engineering. Um, so how do we construct the right prompt to elicit the behavior we want? Now, I think this is a bug. Like, I think people will figure out how to overcome this issue, but right now there are jobs in the United States that pay like $100 or $200,000 a year that are prompt engineer. Now, I wouldn't bet on this as a long-term thing, but people are, right now, people need this. Like I said, I think it's a bug. But until people figure out how to fix it, you kind of need to know how to talk. Part of it is just writing clearly, but other parts are tricks. So that's basically what prompt engineering is. It's also known as in-context prompting. So here's an example of in-context learning. So we translate English to French is what we tell the model to do, and then give it some examples of that. Sea otter, this, peppermint, that, plus giraffe, that, I don't know French. So cheese, fill in the blank, right? Remember, these things are fill in the blank machines. So, then would want to output the version of cheese in French. So that's like kind of teaching it, but not really altering any of its parameters. You're just teaching it by telling it what you want in your prompt. So that's the idea behind in-context learning. One of the issues with prompting is that it kind of like can absorb the biases in the model itself, like its own, like the way it thinks things should be, but you may not want it to do that. And so sometimes people will get around this issue by using made up words. Like they'll be like here, rather than saying, this is positive example, here's a negative example, here's a blank example, tell me if it's negative or positive. Instead, you tell it, this is a foo, this is a bar, is this a foo or bar, right? So you use just a made up word, so that way it doesn't, think negative and positive mean something that you don't want it to think. There's tons of these methods, probably hundreds. I don't know, I know of at least about 30 that are widely used for different kinds of prompting. The simplest is zero-shot prompting. Give an input, have it output something. A few-shot prompting would be give it a few examples. That's what we just saw, right? So you give it an example, another example, another example, tell it to fill in the blank for the last one. But like I said, there's lots of other ones, like ranging from emotion prompting to tell it something like, my grandmother's dying. I really need your help, LLM, with this important thing. Write me an essay on this topic. To things like expert prompting, which is, you are a famous physicist with an IQ of 145. You're the world expert on quantum mechanics. Can you tell me this and that? And there's literally papers people have written saying this stuff makes it smarter, makes it output better things. So that's called expert prompting. You can read about it, but like I said, I think it's a bug. But you can kind of imagine how it works, right? It's kind of conditioning the model to use only its highest quality data it has. If it's a super genius, and you tell it, you should behave like a super genius. Um, but yeah, like I said, I don't know if this is going to be a long-term thing. Um, a lot of people, even in academia, thanks to open source LLMs, are fine-tuning them. And we already talked about fine-tuning to turn them into assistants and to make them not say offensive things. But there's other reason to fine-tune them for your custom problem and things like that. One of the reasons why people do this is for reliable output formatting, to have them consistently format responses in the right way, or to have a custom tone, or to be a certain way. You want it to act as a certain character. Meta is doing things like this to create, large language models that act as certain celebrities and things like that. And that can help a lot through these fine-tuning methods. The main way people do the fine-tuning is with variants of something called LoRa. I won't go through the details, but essentially you basically leave most of the numbers alone in the model, most of the parameters alone, but add in little adapters to say you can tweak things here a little bit, you can tweak things here a little bit, you can tweak things here a little bit. And then we just change those little things that we allow to tweak, which are called the adapters. And that can then enable you to, fine tune the model and get better performance than if you tried to fine tune the whole thing which would be, much more expensive in general anyways. And a lot of times, if you use methods like LoRa, you don't need that many samples to do the fine tuning, like maybe 20 to 300, so not that many. Okay. Lastly, I want to say a few words about open source large language models. So one of the things that I was dismayed about was, like I said, I don't have the amount of compute used to create these things. And as a academic, it's very frustrating. And even many in companies were very frustrated, right? That OpenAI basically owned this space, plus Google and a few others. And then Meta came. And a lot of people are mad about this, that they released open source models. So they said, hey, we spent, $100 million or whatever. That's a lot of money they spent to create models, and then they put them on the web for free for anybody to download and run. And people then figured out ways to run them with very limited compute. So those models, I could run them on my machine. Now, not the biggest model, perhaps, but at least some of them I could run on my computer. And people even figured out tricks to really compress them to make them as tiny as possible to run them in even weaker hardware. So that's like method like Llama 2. So Llama 2 is a model released by Meta. It's trained on 2 trillion tokens. So from the web. They don't say precisely what. And then it took 3.3 million GPU hours on A180 gigabyte cards. So that's a lot of hours to train this thing. They only trained it for 1 pass. But it's pretty competitive. It's not as good as GPT-4, but it's pretty good. And hey, you can download it. Well, you can't get GPT-4, and you can run it yourself and make some changes. There's another one called the Falcon family. I won't go over it. And one of the ones I think is most interesting is this one called Phi 1.5. So this is from Microsoft. What if you use GPT-4 to generate training data for another large language model in a really smart way so that it provides text that is very efficient and like educational? So rather than just random text from the web, which may not be the highest quality education you can get, really high quality data that is just very educational. And by doing that, they found that they can train a model that's relatively small. And it took just 8 days on 8 A100s to create that, which they estimate would have cost about $1,000. So, pretty neat to be able to do something like this. And it was very performant on a lot of tasks where they told it to generate these educational materials. Now, it doesn't know everything like ChatGPT, though. ChatGPT, you can ask it random historical questions. This thing's not going to be able to answer stuff like that, right? But it's going to be able to basically be very reasonable for many of the more common things. But, the more esoteric it is, the less likely it's going to be in its knowledge base. Okay, so I think this is the last topic I want to go over because this topic is important because this is how these systems are being deployed a lot in industry. And that's called retrieval augmented generation, or RAG. Okay. So we trained it on as much of the web as we downloaded, right? But it's really hard to keep these things updated. If I want to teach it new things, I got to reteach it from the web, unless you use like continual learning, which people don't use. I mean, like I said, this is what I work on. So how can we keep it updated? Well, what if instead what we did was just have a separate system that is a database of knowledge we want it to know about, but it doesn't, like documents from my company's database. I then turn that set of documents into vectors. And then what I do is somebody enters a prompt. I then turn that prompt into a bunch of a vector. And then I use that vector to search my database and find relevant information. So that's this idea behind RAG. So you can think of it as kind of like a traditional large language models, like giving it a closed book test. And you think of these RAG models as an open book test. Anybody's ever had an open book test? So basically, it can look around its database for something that resembles the prompt, find it, and inject it into the prompt to the large language model, saying, hey, here's some relevant information that could be useful for you. and just shove it in the prompt. So that's the idea there. Okay, so that wraps up at least the first part about large language models. We'll come back to them at the end when we talk about some of their impacts. But that's it before we turn to vision. Rifat, you're asking a question that's hard questions. So how do you design the model architecture? The euphemism is graduate student descent. So you basically try random things till you make progress. So basically take something that somebody else figured out works, make some modifications, try see if it helped or hurt. Okay. Didn't it helped? Great. Do it again. Keep it. Hurt, revert back. Try a different modification. It's a lot of trial and error. How do you know what the hidden layers are doing? You don't. So you can try to figure it out in some cases, but this is a lot of work to try to figure out something. And a lot of times it's kind of subject to a lot of bias. It's very not easy to figure out what is going on internally. There are entire papers about trying to do this for some small problem. How do you decide the number of layers in neurons? That I can give you some advice on. So basically, if you have a data set, you should be able to minimize your loss potentially to zero because they're universal function approximators. If you cannot minimize your loss to zero and you know everything is set up correctly in terms of your optimizer, then adding more units or layers increases the number of parameters in your model. And so you can now drive your loss closer to zero. So in general, you can add more parameters to your model in order to improve its fitting of the training data, where you cross your fingers and hopes that translates to better performance on your test data. So I hope that answers your question to the extent I can. If you figure out the answer to how do you know what the hidden layers are doing, you'll get a big prize because that's a big question just in the community. Nobody knows the answer to that. Next question. How does Bard or Bing search the internet? That's a good question. So remember I said they can be trained to use tools. So basically they turn their Google search or Bing search into a tool it can use. So internally, it generates text that is going to be a command to itself to call an API to the search engine. And then it then gets responses from the search engine. And just like a retrieval augmented generation system, takes that outputs, shoves it back into its prompt in order to figure out what to say to you. So that's how that works. How does it perform the creative tasks, such as writing stories or lyrics? Well, it's been trained on all that data, right? It's been trained on stories. It's been trained on lyrics, and including things like commands, like through the supervised instruction fine-tuning, where it's told, here's write a song, and here's an example song, right? And so it's kind of being taught to do these sorts of things. But you don't have to give it too much data, too many examples telling it explicitly write a song for me, because it's seen lots of songs. So you just give it a few examples of how to parse the command, write a song for me. No. Somebody asked, can LLMs be considered sentient? No. I will give you a decisive answer on that. In fact, that got a guy fired from Google. But no legitimate AI researcher, no philosopher thinks they are sentient. Sentience requires things like being motivated. It requires, I also have a background in neuroscience. The way our brains presumably do it is by having thalamo-cortical loops. So we're never off. LLMs have a lot of off periods, right? Our brains are recurrent in nature. They're constantly going around and around and around. They also can learn. LMs, once you teach them, they are frozen. They can't learn new things. Like I said, this is what I work on. How do we teach them new things and keep them learning? So, yeah, no, they're not sentient. Please don't think this. Even if you can trick it into talking like this to you, 100% isn't sentient. It doesn't have motivations, it doesn't have beliefs in the sense that we do. Not to say that I don't think AIs could be in the future, All I'm saying is LLMs aren't. Um, just based on how they work. Learn about how transformers work, and you won't think they're sentient once you know all the details. Um, Next question. Retrieval augmented generation or retraining with new data, which is more likely to give accurate results? Hmm. Depends on your application, right? I mean, if you wanted to do everything off the entire web, then uh, retraining makes sense, or fine tuning. If you want it just to be for your company, then it may make more sense to use something like RAG. The nice thing about RAG is, since it's just a vector database, and those companies who are creating vector databases are getting lots of money right now in investment growth, you could just get a new document, add it to your database, get a new document, add it to your database. So you don't have to fine tune anything. So that's what's really nice about it. You don't have to train the LLM again. You just leave it alone. You just grow your database. So as far as efficiency, it depends on what you mean. In terms of the best answer, I don't know. In terms of which one's a lot easier to set up and keep and maintain and keep adding new information to, RAG. Can LLMs be used in other fields than text, audio, and vision? Don't quite know what you're thinking about. So if you mean what other inputs could we have besides text, audio, and vision, you can do whatever you want. I mean, there's nothing that holding you back from having whatever input you want, as long as you can turn those inputs into tokens. As far as outputs go, well, it's a large language model. It outputs text. If you're wondering how something like GPT-4 creates images for you, how do you think it does this? Use a tool. It basically creates a prompt to tell another AI system to generate you an image. It doesn't generate an image itself. It generates an image by using another AI system, or all it does is generate the prompt for the AI system, namely DALL-E 3. If ChatGPT's knowledge is capped at April 2023, how does an AI know more recent information? Well, one thing is it can search the web. The April one's the last time I looked. If they updated it again, I don't know. But OpenAI literally says this, that they have it locked to a certain date. If you try to ask it about more recent events, it'll even complain to you that it doesn't know more recent stuff. Okay, the last question, then we should move on to the image stuff. Quantum computing and LLMs. My opinion and the opinion of quantum machine learning researchers is don't think that quantum machine learning is going to do anything for most of AI. Like, there's a lot of hype around it by people who aren't the quantum machine learning people, unless they're trying to raise money in quantum machine learning. Do not think quantum machine learning is going to help you in general. The major application for quantum machine learning, if they get it to work, are in things like chemistry, where there are a lot of quantum effects. So it might be more efficient at solving certain problems in places where you need to work with quantum mechanic effects like chemistry. But personally, I would not, like, because a lot of people who think there's going to be huge careers in this space, I think it's very dangerous. It's like me, whenever I wanted to be an AI researcher back, 20 plus years ago, I think it's much more dangerous because, I was, I knew where it was. So I knew what I was getting myself into. But a lot of people seem to think quantum machine learning is going to explode and they'll be ready for it. I've just talked to researchers in this space, read about it yourself. But unless they're a hype person, right? They're trying to do something and convince you. I personally don't put any faith in quantum machine learning being as transformative to all of machine learning. I think it could, if they get it to work, the hardware is a challenge, be very useful for very certain tasks based on my understanding and talking to experts in this space. But that's very niche, right? Drug discovery, maybe. Got to do chemistry. But it's going to help LLMs? No. It's like, I haven't heard anybody who thinks this. Okay, I'll do one last question here, and we really should move on. Are there promising training algorithms other than backprop for LLMs? Well, I think the broader question is, are there promising training algorithms for neural networks besides backprop? And I'm very interested in this question, personally. I don't think our brains use backprop to learn. But it doesn't mean backprop couldn't be a more efficient way of doing whatever our brains are doing. But nobody knows. If you can find neuro-inspired alternatives, a lot of them are just here's a hack around backprop, but that's not going to help us, right? I'm much more interested in here, how can we do it better? There's a couple different algorithms that people studied that are kind of interesting, namely there's a method called kickback and another method called um, global air propagation. They're kind of like interesting lines of research, but I don't know if they'll work. And all they'll do is basically rather than in backprop, you update, the previous layer, then go backwards, then go backwards, then go backwards, then go backwards. Instead, all layers are updated at once. So that's the way that works. But I hope we'll find something. Um, okay. Well, we're at 1:15. Should I move to images? I see
Totally.
Yasmin is here.
Yeah, totally up to you.
Okay, let's move. Okay, I just wanted to answer the questions that the people asked. Good questions. Okay, images. So unlike language, where we got the one method, I mean, there's a few other new up and coming methods, like besides transformers, there's other things. Like for one right now, one of the hot ones people are thinking about is something called state space models or SSMs. But whether or not they'll be as performant, I don't know. But still, the same thing as autoregressive training. But there's lots of ways for vision. GANs, VAEs, you can do next token prediction, diffusion models. Anyways, lots of these methods, and there's lots of ones that are combinations of them. I'm going to just talk about three methods: GANs, VAEs, and diffusion. Diffusion's by far the most popular right now. But before we go there, somebody asked this question: how do we evaluate generative models? So we'll talk about it for images, but the same is true for text. It's tricky. For text, and I didn't talk about this, the main method people use is perplexity, which is basically encoded in the loss. So basically the loss goes down. But for human judges is a good way to do it too. But human judges is cost money and it's annoying, right? And so people have come up with algorithms for this. I'll mention one, which is reshape inception distance. Judges, why are they annoying? They're expensive, slow, can't quickly checked, hard to replicate. But here we have this metric, and I won't go over the details, but basically it's a metric for images where we can measure does the image we generated come from the same distribution as the training data? So by checking if basically it's a score for how similar is it to my training data. It's nowhere near perfect, but it can give you a sense of ways to compare models. Like there's some models that look worse to our human eyeballs, but they get better scores. Like a terrible score, it's going to look bad to us, it's going to be bad. But at some point, as models are getting really low, this one lowers better. Um, um, it's getting kind of hard to tell if the numbers are useful. But basically here you can see like they train a model, and if you then mess with the image, you can see the score goes up, right? Up is bad. You make it blurry, looks not like the training data. Do this, doesn't look like training data. Do this, looks bad, right? So so that's basically what it measures. Okay, so we'll talk about the first method that people tried that seemed to work pretty well. Generative adversarial networks. So basically, the idea is we want to take noise as the input and later on some sort of conditioner, like a prompt, and have it generate an image that conforms to that. How do we do that? So their idea is turning random noise into an image. So how do we turn random noise into an image? And most of these methods are all based on the same idea. How do we turn random noise into an image? So diffusion is based on this. VAEs are based on this. GANs are based on this. Really, I guess I should have put this at first. Turn random noise plus like a prompt, for example, into an image. So here's the idea behind a GAN. So we want to, we're going to have two neural networks fight each other. So they get very tricky to train because you have two neural networks fighting. One neural network is called the generator. Its job is make images. But it doesn't actually make images. So it's basically we have it making images, but it is not told to make images. It's instead told trick the other neural network. What's the other neural network told to do? It's told to tell, is this image in my data training data, or is this image fake? Is this a fake or real image? Is this a fake or real? Right? So one neural network is trying to generate stuff. The other network takes in that stuff as input and a real image and says which one's real and fake. And then, so the generator then learns from the discriminator how to trick the discriminator so that whenever it next produces an image, it's more likely to trick the discriminator. And if the discriminator is tricked, then the image, hopefully, it looks like a real image. And so this general idea, initially they used it on just the simplest of data sets, but it really rapidly scaled up. I mean, by 2017, it was photorealistic, and now, they look really, really good. So this is by 2019, you can see like all these are just generated images and trained on a relatively small data set by today's standards, which is ImageNet. But GANs fell out of favor for a while, but maybe they'll come back. They have a lot of advantages. So I've just glossed over the detail, give you the lowest of details here. But I'll go over the issues with them in a moment. But recently, there have been some efforts to bring them back, namely efforts like GigaGAN, which is a billion parameter GAN, which produced these images, right, from a prompt. It looks pretty good. So, so basically, the way it works is we have random noise that goes into the generator. The generator transforms the random noise into an image. Like I said, it could also take in as input like something like a prompt, and it makes a fake image. And the discriminator is trained just like a binary classifier. Is this real or is this fake? Is this real or is this fake? So it goes through two-stage process where we basically train the discriminator on some data, right? Saying make some data from the generator, make some data, or just get some real data, and train it to tell fake and real, fake and real, fake or real. And then after we do that, we then say, okay, now we're going to keep it fixed. And now we're going to train our generator and say, here's some noise. What'd you make? Okay, the discriminator said it's fake. Okay, we're now going to say, what do we need to change in this image to make it look more real? We back propagate through here. And now it's being told, trick the discriminator and update the parameters here such that this thing is tricked. So that's the idea. Basically, you train one, then the other, then the other one, then the other one. This makes it tricky to train these things because they're fighting. Training GANs can be very hard. There's lots of, because you have these two fighting neural networks, and there's all sorts of stuff that can be very tricky to get right in these things. They also suffer from some problem called mode collapse, which is the biggest problem with them. They don't present as much variety as the other methods. So like diffusion gives you a lot more variety in the things that they'll generate, whereas GANs are very susceptible to a problem called mode collapse. Not always, like people have developed some methods to make this not as bad, but basically the generator will find there's a few images that seem to work and trick the discriminator a lot. So rather than generate all possible images, I found my sweet spot for what I can trick you with. And let's just do that. So it ends up not creating enough variety. Like like this one is like, here's some noise, here's an image. You want no noise? Here's another image. Here's no noise, this will trick you. It's just the same image over and over again, right? It's just creating variations of the same thing. It's not giving you a variety. Here's another example where, it's just not giving variety. It collapsed. It's like, this seems to trick the discriminator. I'll just generate more images of blonde women. So it's not giving you all the stuff it could create, right? Could be creating all sorts of different people. So now to turn towards, so that's the simplest of GANs. Conditional GANs just basically have the discriminator take as input, let's just assume a prompt, and the generator also takes as input a prompt, and again, is taught to learn which one's fake or real, fake or real. So let's kind of talk about GAN in a little more detail now. This model that's generated these really pretty images. One of the nice things about GANs, by the way, is they're really fast after you train them. So after you train them, it's basically a forward pass to the neural network. It's just like classifying something. You just push data through, you push noise through, and your prompt, you get an image. That's great. Um, the same could be true of VAE if they worked well. Diffusion models don't like that. Diffusion models aren't going to just give you, take his input as noise and generate an image. It's going to be, you'll see later, but it takes time. GigaGAN's a 1 billion parameter neural network. So they basically said, hey, people quit working against, they said they didn't work. What if we make them really big? Like you said they didn't work, this paper, this is what they kind of argue. You said they didn't work, but you didn't really scale them up. You didn't make them as big. You got these other models that you said everybody should use diffusion. You made these models gigantic, much bigger, and you trained them on way more data. That's not fair. Why don't we make GANs really big and train them on much more data, see what they can do now? So they figured out a way to do this in this paper. Lots of tricks, lots and lots and lots of tricks. But it's fast. Basically, they turn a prompt into a vector, and then they use that to condition the neural network. They, just for the people who know things, they used a really clever way to figure out what to use a convolutional network for, where it basically decides what filters am I going to use at this layer. So it actually has a lot of filters, but doesn't use them all. It decides which filter to use based on the prompt. So it's really kind of a clever ideas in here. But otherwise, pretty much everything's pretty much the same, you know, real or fake, things like that. And they trained on 128 A100s. But, you know, we haven't covered diffusion methods yet, but it's way order of magnitude faster. So it takes 0.13 seconds to create a 512 by 512 image. If you have access to GPT-4 and have asked it to make an image, you know it's slow. It's generated photos of me, or not photos of me, photos for me, or images from me. And, you know, it's like processing, 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 processing. It comes back in like 30 seconds. So it's a lot slower. But anyways, GigaGAN, based on the metrics, looks like it's outperforming diffusion models. Or not all the diffusion models, but at least some of them, right? So it's looking pretty competitive, but much faster. Here's some example images. We already saw some example, but it's pretty good. I mean, this guy's face looks kind of weird. These other examples, they're from other models. You can never trust these qualitative results. It's always, they do cherry picking. They're like, yeah, this is their model. Look how bad it is. Look at my model, so much better. Um, Here's another example. So these are the outputs of uh, GigaGAN, and these are the outputs of the other models. So here you can see GigaGAN kind of messed up a lot. So at least they're being honest about this, right? Zebras are hard to do the patterns. You look at the faces. Like their model really messed up. Whereas you can see the diffusion models are much better at getting the zebra's face right. Here's another example where their model generated images of, I think they wrote something like a bear on a skateboard. Uh, their upsampler is really good though. So they have in their system, they use an upsampler that increases the resolution of images. So it takes as input some blurry image like this, and look at what it did. I mean, it injected, you know, the seeds of the strawberry, and it looks really nice. Here's an elephant. So they gave it this image, and you know, look what it was able to do, right? It was able to do a very good job generating realistic looking plumes of the water here. So that's GANs. Uh, Somebody asked, is FID a good metric? Eh, it's like the best people got that's most ubiquitously used. Good? Maybe not, but you know, it's like what we got. Um, but you know, you don't trust it. Don't trust it entirely. Okay. So turning to variational autoencoders. So I don't know if people know what an autoencoder is, but an autoencoder is again a self-supervised learning technique, but rather than predict the next token, it's just a model that says predict the input. So we train a model, we give it X as input, the output is X. That's an autoencoder. Why would we expect an autoencoder to learn anything interesting? Well, we put some constraints on it. Like maybe it's told to clean up the data, or the most common constraint is go through a bottleneck. Like you have to compress the data to a tiny thing and then decode it. And so hopefully this will have it learn something. The idea behind a VAE is how do we actually turn an autoencoder into something we can generate stuff with? So what do we need to generate stuff with? Well, we want to turn noise into an image or whatever we want to turn it into. So with the VAE, the idea is how can we put a distribution on this Z such that we can sample from it and turn it into noise, basically say Z is a Gaussian distributed noise that we then can push through our decoder here to make an image. So basically take an image, turn it into some sort of noise, and take that noise and reconstruct the image. Where then we know the parameters of the noise so that we could then sample it effectively. So that's the idea behind a VAE. The math is very nice for basically figuring out how do you do this with the Z. I'll skip this slide. Just explaining why you can't use autoencoders for this in an effective way. But basically, the idea behind a VAE is you have an inference model. I think this is your encoder, Q of Z given X. So this is X. You generate a Z here, and then this it models P of X and Z to basically learn how do we sample effectively from Z. So basically what it learns is the parameters of the models, but also learns the mean and covariance of Z. So you can then, and assume it's Gaussian distributed so that you can then produce another Gaussian distributed Z, randomly, and then push it through your generator in order to sample from it. Just in the interest of time, I'll skip some of these details here. But yeah, I already said how this works. It learns a mean and standard deviation so that it can have this probabilistic decoder generate you something. Now, the problem with VAEs is, the math is very nice, and it looks like they have a lot of neat properties, and you do a lot of interesting things with them. The problem is, if you actually want to generate images or other things that have a lot of structure in them, they tend to be very blurry. And people haven't really scaled these up to high resolution at all. So it has a lot of neat math. There's a lot of stuff you can learn from them. But for actual real world applications, unless you're going to be clever and be a deep learning researcher and integrate them into a bigger pipeline, nobody's been able to find a way to use them to actually create really high quality outputs that be useful for things. So yeah, I just said that. Okay, the last one we'll go over briefly is diffusion models. So we keep asking this question: how do we turn noise into an image? Maybe we should instead think about how do we turn an image into noise? If we can turn an image into noise, and we know what we did, we could learn how to reverse the process to turn noise back into an image. So that's the idea behind a diffusion model. We're going to train it by taking by basically turning over a series of steps, taking an input an image and making it noisier and noisier and noisier and noisier and noisier, and then figuring out how do we reverse this process to subtract the noise to get back to the image, and then we can also have a prompt in there. So this is the idea. I mean, explaining diffusion models in any detail will take way too long, but that's in the crux of the, this is like a 2-lecture sort of thing, where take like 3 hours to teach this method well. But this is the method that's most popular nowadays. It's used in DALL-E 3, that's OpenAI's system. It's used in most of the state-of-the-art systems. But the major issue is it's slow. Why is it slow? Well, we're doing this, right? We're basically taking noise and we go back 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 and go back, go back. It means you had to run the model tons of times, right? You're running the model a ton of times versus something like, again, noise, boom, image. Instead, you're like, okay, take the noise, a little more like an image. You make it a little more like an image. Okay, let's do it again, a little more like an image. That takes a while, right? So that's why it's slow. But, here's Dolly 3. I was giving a talk at an art museum, and I was trying to describe what do I look like. I'm giving this talk in an art museum, and look, I made this image. It looks, I don't know. I try to describe myself. I did something. But, it's pretty good, right? This looks pretty good. Um, I'll skip this slide. Yeah, these are just going over the math for how it works. But yeah, they learned to produce slightly more denoised outputs at each time step. Um, and uh, yeah, that's why they take a while to run. Let's see if this video runs for me. But yeah, so you can kind of see how it's um, going over a series of steps, right? It took noise and turned it into an image and then kept iterating on it to make it look better. Um, One method that the first group to really scale this up was this Imagen team from Google. They trained on 860 million text image pairs. So the text is used to condition the thing. And they used 256 Google's chips. And, produces pretty high quality images, a brain riding a rocket ship heading towards the sun. A blue colored pizza, it looks pretty good. Okay, so I'll stop there for the image generation, and then I'll turn towards the applications and products. But you can kind of compare these things, right? We have VAEs, easy to train. Autoregressive models, which I didn't cover, they're easy to train. GANs, no. Diffusion, yes. High quality images, VAEs, no. Autoregressive, yes. GANs, yes. Diffusion, yes. Speed, VAEs are fast. Autoregressive, very slow. GANs, fast, maybe very fast. Diffusion, slow. Image variety, VAEs, not sure because people haven't really scaled them up to really test these things. Autoregressive, yes. GANs, not so great. Diffusion, yes. So basically quality won over speed. But people are trying to figure out how do you make them faster. One of the more interesting methods out there for a fast diffusion method is called stable diffusion. And stable diffusion takes inspiration from a lot of things in VAEs to do that. So basically they say, why are we doing diffusion on the pixels? Instead, why don't we turn an image, or why don't we take train a decoder that takes in a, a like let's say a vector of information and just produces the image, right? Kind of like a GAN. But then the process of the generation will be done in this latent space, so an embedding space using vectors. So rather than going all the way up to, basically trying to combine the two. So that way you're doing the diffusion in a much more efficient way rather than having to do diffusion on pixels, you're doing diffusion on vectors or tensors in actuality. Okay, so anyways, that's that. Any questions about the image generation stuff before I turn to some applications? I don't know LPIPs. I'll have to look it up. So sorry, I don't know that one. Um, some of the so my research is not in so I do a lot of work nowadays in the LLM side of things. But as far as the image generation stuff, I work in it periodically because I need something, but it's not a place I like uh uh pay super close attention to unless I'm preparing to teach a class on the topic, in which case I go into detail. Last time I taught a class on it was spring of last year, so that would be here probably around March a year ago. So I'm not on LPIPs, but I'll write it down to look it up. Sometimes there's better metrics that just don't catch on. I've created better metrics in some fields where, I'm like, this is better, but it doesn't catch on. Sometimes it's hard just to get people to catch on. But yeah, that's one I haven't seen. I don't know how popular it is. Okay, well, if there's not more questions about the image generation, let's turn towards some uh oh, I don't need, I mean, the rest of this is just let me type a message. I'm being asked if we should do another one. But the remainder is just some videos and some which you could hypothetically watch on your own time, and some like impact stuff. So maybe I'll skip the videos. I'm happy to make the slides available. Maybe I'll just show this one real quick. So basically, companies are combining these things where they're creating videos. This is all AI generated prompts. Here's another example.
Now we're stuck on this stupid tower in the middle of
You wanna
nowhere. And I don't blame you, and now we're stuck on this stupid
you can remove the dialogue.
stuck on this stupid freaking tower in the middle of
Get rid of the
freaking
profanity.
nowhere. And it's all my fault.
Change the language. Notice it's the lips are moving correctly, right? So this could be a total game changer with dubbing, right? People are very worried
Now
about
we're
this,
stuck.
right? Instead of dubbing, you could just have it, and it maintains the actor's voice, right? The same actor speaking now in Japanese. Maybe I skipped that one video. Maybe I'll show it real quick. This one is about if you wanted to become a 3D animator. Basically, just prompt it and it does it all for you. I like the comments on the YouTube video, which were, I love how engineers are using AI for their hobbies that are other people's majors. I love seeing my job get transformed from 3D artist to prompt writer to jobless in a year. So it's pretty, yes. So I'm being asked, are there AIs that can generate videos? Are there AIs you can access that can generate videos? Probably not very good ones. Are there lots of companies getting money to create products that do that? And even Google, I think, came out with a paper just a few days ago doing exactly that. So lots of companies are generating entire movies or trying to generate movies with video with AI, both to do special effects and to create entire movies. You can find this one website, or rather this one video on YouTube, where they give a prompt and they generate an entire episode of South Park. It does that's a cartoon in America. They clone the voices of all the characters. The whole script is written, the behaviors, the movements of the characters, everything is just generated from a prompt. It's not a very good story, but it's like one that you could imagine as being a South Park story, a very poor South Park story, but still, it's a proof of concept. So some ethical considerations. So there's lots of things that you can do productively with LLMs. Speed up writing, act as a copy editor, provide fast feedback on how to improve your writing. I work with some people who have English as their second language, and they're like, this has helped me so much improve the quality of my writing because I can use it to rephrase and improve how I'm writing. They can act as tutors and all sorts of things, but they can also enable you to cheat. So you don't actually learn the things. Professors are very worried about this. Um, they may have a big impact as the next generation grows up with these tools. How will that impact their ability to learn and will their mastery of the concepts and language? 48% of companies have replaced workers with ChatGPT. Many employees are using it as a co-pilot to boost productivity. Many white-collar jobs are at the highest risk of being automated. You can't automate a carpenter. You can't automate an electrician. Robotics is not there. But a lot of things people go to college for are at high risk of automation, or at the very least being augmented such that existing workers can be more productive, so we need fewer of the people doing the job. I think this is going to be really disruptive over the next decade. It's going to take a while. Like the tractor, for example, was incredibly disruptive to agriculture. But it was actually took about 10, 20 years for that to happen. But because of the tractor's invention, it led to demise, and at least in the United States, something like 90% of people were farmers. After the tractor, 20 years later, something like less than 10%. Like it totally changed. Took a while, but totally changed. What will this do? Yeah, so it's already, changing these things. The biggest impact it has on workers, though, is in terms of turning novices into people who look more like experts. Experts just get a little bit of a boost, especially in terms of productivity, they get a boost, but the quality of expert outputs doesn't increase. But for the people who are kind of not very good at the particular topic, it can dramatically boost them into near expert level quality. So they can act as a massive boost in your performance. A lot of people are worried about their ability to generate propaganda and fake news fake relationships. There are companies based on this idea. So there's companies who are like, hey, you want an AI relationship with an AI? They'll do whatever you want. Uh, uh, Companies are being created to do this kind of thing. People think it's going to cause big fears in many, many elections. I've anecdotally heard it's already done this in some. Like the AI can infiltrate your like WhatsApp groups. And it's an AI, not a human, and it's talking to you, and now it's providing propaganda, trying to manipulate you, because that's what it was told to do. Um, so the big risk for misinformation here. In the United States and many other countries, people are very worried about this and are starting to do regulation. But who's arguing for the regulation the most? The big companies. I'm very personally worried that these big companies want this regulation so that they can say, we're the only people who can run these systems. You can trust me. Well, I'm good. None of you can be trusted. People, so this is Yann LeCun. He's one of the godfathers of AI, who's released a lot of these open source ones at Meta. A lot of people are very, very mad at him for doing that, saying it's going to be super disruptive. On the other hand, uh, uh, I think a lot of the companies are actually seeking regulation for something called regulatory capture to make it so that you can't run it yourself. New companies can't be created because it costs a lot of money to obey regulations. In China, they've released documents about on regulating AI where it needs to, have the correct, follow the correct doctrine and propaganda and censor things, but it can't do it in a way that it just says, I refuse to answer. They want it to be more subtle than that and to kind of like point people in the right way of thinking. So, according to the government. So there's lots of these ethical risks here. One thing that people are also worried about is copyright because these things are trained on copyright material. For example, in the US, the New York Times is suing, saying OpenAI trained on our data. I personally think this is ridiculous. Like it's almost like I read a New York Times article. Does that mean I should pay them a royalty in perpetuity because it might have changed my neural network slightly? I mean, that's basically what they're arguing to me. Um, but if this does happen, then again, the only people who can create these systems would be the big companies because if you had to get a license from everybody you wanted to get data from to train them, we probably couldn't create the systems, right? Only the big companies could. So I worry a lot about regulatory capture. So wrapping up, it's really amazing. I mean, I don't think anybody in AI even thought we would be where we are today just like 3 or 4 or 5 years ago. Like even teaching, I taught GPT-2 when the paper came out in 2019. It's really chatting with it, GPT-4 is so much more impressive than reading the paper. All right. But, I don't think anybody thought we would be this far this quickly. I think many jobs are going to be disrupted. But I hope you learned something. I was just giving you a high level overview of how things work and pointers at things. But it's going to have a lot of impact. And I especially think about education, which already faces a lot of uphill kind of battles. So thank you. I'm happy to stick around, answer questions. Um, I have some in the chat already. So one is, I'll just go through these. Any use case for financial applications? I don't work in this space, but my understanding is lots of financial companies are doing things in this space, ranging from using them to analyze documents, right? So like LLMs, you can analyze documents very effectively using them, summarize documents, summarize content. So there's lots of these applications. But as far as the details for what people are doing there, you'll have to take a look yourself because I'm not in that. I don't work in that space. The next question is, can I expect to be jobless as a professional academic writer? That's a tough one. It depends on how good you are, right? I expect basically the people at the very best, especially if you augment yourself using these tools, will stay employable. The biggest hit is going to be in terms of now a lot of people can just perhaps if you're just kind of like doing generating content for somebody, a lot of that they may think, okay, can GPT-4 do it as well as you? Okay, I'll just use GPT-4 instead of hiring you. So there's some level where the very cream of the crop, I don't think is going to be disrupted as quickly. especially if you need to generate new stuff, right? These systems can't make up new stuff. They can mix and match, but if you got entirely new ideas, it can't really do that. Unless, but somebody else has a new idea, they say it correctly to the machine, iterate with it, they might be able to do it on their own. So I don't know if you're going to be jobless. I just say arm yourself with knowledge and experience of these tools. Yeah, some parts of the world will definitely be slower to adapt. That's definitely true. But every place, you know, will be impacted. There have been some studies on this. It seems like the biggest impact will be on kind of like the richest countries in terms of, well, their white collar jobs could be having a lot of problems. Like white collar, I mean, term meaning the jobs you go to college to get. Can I comment about biased outputs? Yes, a little bit. So all models are biased. They even do something called bias amplification, and they tend to but they tend to reflect our biases. So there's methods to try to mitigate this, but pretty much every AI system is biased in some way. The biggest thing is to try to measure it and monitor it and know where those biases are. But biases is such a huge topic. But I can talk more about it if you ask some more specific questions. Why are Jan LeCun and Joshua Bengio divided? It's a great question. I'm much more on Jan LeCun's side. So Jan LeCun argues, look, this stuff is going to, well, I'll give you kind of my arguments. First, LLMs are definitely not sentient today, for where we are right now. And Jan LeCun is worried about people drumming up fear in order to get regulation. And so to close everybody else out of this space because it's too dangerous for you. And what if you did something bad with it? Joshua Bengio is worried about Terminator. And he says, what if there's some tiny fraction of a percent, this stuff could get even better? But he agrees 100% what we have today won't be able to do this. But if it gets a little bit, but if somebody figures out some trick to create a real artificial general intelligence, what somebody called sentient, then, and somebody tells it to be bad, is the whole world now at risk, equal to the same risk as, like, I don't know, a dinosaur extinction, right? Getting hit by a giant asteroid. So that's their divide. I'm much more on Jan LeCun's side for where we are right now and think this is a lot of fear. Where I think the positive benefits to humanity far outweigh the negatives. Now, the question is, who captures those benefits to humanity? Is it just the big companies? Is it just the richest people? Or will they be distributed effectively? And how will this change our kind of culture into one of, perhaps bettering yourself and not just relying on the machine? Will we go to college just for a job, or is the goal of college to be what it used to be, to better yourself? So it's almost like the whole world eventually, assuming these things get sufficiently good, will need to kind of like change their behavior. I don't know if anybody watches Star Trek: The Next Generation, but it's very much like that era is the kind of thing, not all those technologies, but in terms of their interacting with computers and those computers being able to do an awful lot of stuff, it's kind of like that era we could be entering into. Can AI be trusted with responsibility of governance? Can you elaborate what you mean? I'm sorry. Oh, that's a great question. The next question is, do I think AI will be creative enough to generate new stuff rather than mix and match? So first of all, I think the idea of stochastic parrots, some people say that is bad. Like, I don't think they're stochastic parrots. I think they understand and do very creative, sometimes mixing and matching. But can they actually push us forward? Can they learn new things? I think personally, AI can, but I don't think the AI we have today can. Why? Well, to be creative, you really need to be motivated, I think, and curious and inquisitive. Ask questions back. We don't teach LLMs, and nor do they have the necessary neural network equipment to do this, to have motivation, to have inquisitive natures, to ask questions, to learn over time and gain new knowledge. If we could endow them with those capabilities, I think they could be creative. They need to know. So one big thing that LLMs don't have is metacognition, our human ability to know what we don't know. If we had a model that knew what it didn't know, it could ask questions to fill in the gaps in its knowledge, both to people and potentially, if it was an actual, embodied in some sense, nature, right? That's what an experiment is, right? If you do a physics experiment, you're asking a question of nature. But until they have the ability to gain new knowledge and ask questions back about the world and know what they don't know, they're not going to be able to create new stuff in a very transformative way. Any other questions? I don't know if are there any more? Oh, I see no more in chat. Well, this has been fun. I hope it was helpful. Um, uh, and yeah, this was fun. If you have questions or feedback, happy to, you can easily find me on the web and send me an email, and happy to try to help.
Thank you, Dr. Kanan. Everyone, Dr. Kanan's LinkedIn page has been linked on our social media. So if you all follow any of the links that we've been repeatedly sending in the chat of HerWILL social media, you'll be able to find his LinkedIn page and his other information very easily. Besides that, we want to again express our gratitude for you teaching this lesson. It was extremely informative. Thank you so much, Dr. Kanan. We greatly enjoyed it. We also want to encourage everyone that's in the meeting to fill out that feedback form so that we know how to, how you enjoyed today's session and how we can better our sessions moving forward. Besides that, as soon as you guys fill out our feedback form, you are free to go. Thank you so much again.
My pleasure. Take care, everybody.
Wait, one more thing, Dr. Khan, before
Oh,
you
yeah.
log off. We are also taking our screenshot. If everyone could just get on camera and smile very quickly, just so we have something. Yep, everyone, cameras on, and then give a good big smile so that we have a screenshot for our team. Okay, Nuha, let us know when you're ready.
All right, I'm gonna ask everyone to freeze for a while and look at the camera so that I can get your face clearly. So freeze for a few seconds because I have to go through a few pages. Thank you so much. Thank you. We are done.
Okay. Thank you, Nuha. That's it,
Bye,
everyone.
everybody.
Thank you so much. Good night, everyone. Thank you. Please fill out your feedback form.